Is it recording now? Well, boy, I could tell you some stories on my recording capabilities. I'll just tell you one real fast. I took my brother-in-law turkey hunting one time, and I was going to let him kill a turkey. I'd scouted this bird. I knew when this bird was going to eat off the ground or fly into a tree. I watched him this long. I don't have that time in my life now, but so yeah, I worked it up perfect. I had the turkey coming off the roost. He comes around this way every morning. We set up, hit a couple of calls. He comes right up. I've got the camera on the whole time. I told my brother-in-law, I said, as soon as he raises his head, you can take him, blow up, bam, kills him. I mean, just, he's a big old bird, everything's perfect. And I look down there and it's on pause the whole time. It'd been the perfect hunt on video, it was just writing it out, but no, it was on pause the whole time. I noticed it when I asked him, tell me, sir, what's the secret of your success? He said, well, it's the guide service. And I looked in there and said, pause. We didn't get the guide service in on that. So anyway, this chapter is finishing up kind of the skeleton with movement of skeleton with muscles and a lot of invertebrate situation. Cilia and flagella are ways of moving, which in lab this week, for those of you that's going to actually come, we will look at different means of movement in the protozoans because we have a fresh batch of protozoans that's been shipped into us. We're going to look at them while they're alive and well, and there'll be some with paramecium that have cilia. We'll have euglena with flagella. We'll have amoeba with pseudopodia, and we'll be able to see all this on the microscope and look at that this week. And those are all means of movement. When we go into the actual process of muscle movement, like the three muscles they're mentioned in this chapter, cardiac, skeletal, and smooth, you know, it's skeletal muscle that moves our skeleton around. And that takes care of our endoskeleton. And there are different kinds of muscles in different invertebrates, but a lot of it's a striated muscle. That's what they call it. It's just a striated muscle, which is skeletal muscle for us. So, with that said, I want to look at what it takes for muscle movement to occur. And this is, it says chapter 12 notes at the top of this. I didn't scan it down there where you can see it. But this actually comes out of the physiology book, same lecture I give in physiology, so this does prepare you for the next class. If we're looking at a skeletal muscle, and a quick view of skeletal muscle, picture-wise, which this is actually out there on my website, is that picture right there. Skeletal muscle makes up 40% of your body mass. I mean, it's got to be quite a bit there to move us around. It is striated. You can see the lines up and down. The muscle fibers are running this way, but we have a striation, so it's a striated muscle. It is voluntary, which means that you can control skeletal muscle. Now, you know, reflex, you don't really have conscious control of reflex, but it's skeletal muscle that's responding to that. Like I said, it is voluntary. It makes up 40% of your body mass. My favorite example of this muscle is your tongue, because you're supposed to be able to control it, right? It is voluntary. But some of our tongues just fly off the hammer, and it's like, where did that come from? You know, that was an involuntary response. But this is skeletal muscle, and name a skeletal muscle besides tongue. I just gave you that one. Biceps, triceps, quadriceps, all the muscles groups that we're familiar with that fits this muscle. All right, so this is a picture we'll be looking at in one of the labs. So what makes up a muscle? We have two different sets of proteins. We have myosin and actin. These are the contractile proteins. Myosin is a thicker protein, and actin is a much thinner protein. Those two in themselves allow muscles to actually contract. Now, those two eventually into myofibril, specialized structure, so those two are in a structure which makes the muscle fiber itself, which several fibers make up the whole muscle. Now, let me talk about that just a little bit. We don't just say, okay, we've got a biceps here, and old Joe with his biceps can pick up 450 pounds. Well, you think the first day Joe decided to pick up 450 pounds, he could pick it up? he probably had to work into that. And what happens is we can pick up a small book or a notebook, and we can carry that notebook around for a long time, can't we? But when you pick up something heavier, you may have to set it down and rest every now and then. And what happens, each fiber has enough strength to do a job. If it takes 5 fibers to do a job, when those 5 fibers get tired, they'll recruit 5 more fibers in the same muscle to take on the duty. And so you can carry a small object for a long time. They'll keep recruiting and keep recruiting. And by the time we get back to the first 5 fibers, they've regenerated themselves and they're ready to work again. It's like tag teaming jobs. Well, if we're picking up a heavy desk, we're going to take them here over there. How many times we get it halfway there? Let's rest a minute. Then pick it up. That's because we're using every fiber. And when they're done, you better set it down or somebody's going to drop it. So, and then we get back to old Joe here that he always wanted to lift equivalent to his body weight. That was my goal at one time. And back when I weighed 160, I could do that. It's just my weight overcame my strength at some point in college years, you know. So you start building strength in your muscle, which each one of these has their own mitochondria, their own energy levels, and when you start putting more pressure and time and I guess it's a term I'm looking for here, when the muscles get used to doing more, they'll start building themselves up to do more. They'll make more mitochondria, which gives them more energy. They'll store more energy, which you can get more done. So, and this muscle will get bigger to do its job. Now that's called hypertrophy. Now if you're 5 years old and you grow 2 inches between 5 and 6, you created hyperplasia. You increase the number of cells. In hypertrophy, you increase the size of your cell. That makes sense? If a bodybuilder is lifting weights, he's building the size of a cell. He's not increasing the number of cells in that muscle. He's increasing the size of the cells in that muscle. And those muscles are used to working, so they look bulkier because they stay ready to work. All right, I'm going to explain that a little bit more as we go. As we come on down, we have the functional unit of skeletal muscle, which is a sarcomere. The functional unit of anything is the smallest component that actually can perform the functions of the organ. You have an actin binding site and a myosin binding site and an ATP. ATP is energy. If we consume a candy bar with sucrose in it, the body will turn it into glucose. Well, the cells will take glucose and make ATP. ATP is adenosine triphosphate. It is our usable form of energy. And we got to have energy to do all this, right? Now we make it to troponin and tropomyosin. Troponin and tropomyosin are regulatory proteins. They regulate whether actin and myosin can slide past one another or not. That's what they're doing. So this whole theory of muscle contraction is called the sliding filament theory, and they talk about it in the text as well, which means actin and myosin are always overlapped. Troponin and tropomyosin block them from sliding past one another. Tropomyosin's in between them here. When a contraction needs to happen, calcium triggers that contraction. Calcium is stored in the muscle. It's stored in the lateral sacs right here, in the lateral sacs of the sarcoplasmic reticulum. It's released. What triggers the release? Either you telling your muscle to do something or a reflex action triggers the calcium release. It attaches to troponin. Troponin then pulls tropomyosin out of its blocking position and allows actin and myosin to slide past one another and shorten and thicken. So the sliding filament theory is a chain reaction. Without calcium, none of it happens. So I ask a question on the physiology test. I ask the question, at rest, is actin and myosin always bridged or always crossed? And the answer is yes. If that muscle is used a lot, they're more crossed or they're more bridged. Overlapped is another term. They're more overlapped. If that muscle's not used very much, then they're overlapped a little. Does that make sense? Because is it not easier for this muscle to respond from this distance, getting the job done, than this muscle respond from this distance? Which one's gonna hurt you more tomorrow?
Far one.
This distance or this distance? Yeah. So when we find those muscles we don't use very often, they find you the next morning when you actually used it. You think you created some friction there that maybe moved a little rust out of the joints, creak, squeak, squeak, and the next day it's like, I'll tell you something with age, it doesn't get you the next day. 2 days later. I mean, the next day you hop out of bed thinking, I'm done pretty good today. The next day you fall out of bed, so what happened? You've got one leg working. It hurts. Any way it goes, it hurts. All right, so that's how a contraction occurs. Now, magnesium is necessary, as it says here, the sarcoplasmic reticulum having the calcium available. We've got to have calcium, or no muscle contraction occurs. And then the relaxation part is as simple as this. We use an active transport pump, which requires energy. We remove the calcium. Once we get the calcium out of the way, troponin and tropomyosin go back to their blocking position, and the muscle's back at rest. Again, if it's a muscle that is used a lot, it's overlapped more, which makes somebody look like they've been working out. The muscles stand more bulged all the time. If it's a muscle that's not used much, it may not go back and overlap as much as we want it to. Maybe just a little, but the more you use it, the more it'll rest in a more overlapped position. So your muscles literally can do what you demand of them, within reason, of course. You don't want to think you're going to build muscle hypertrophy in 3 days. You know, to build muscle, you got to break it down. That's why people say, well, I lift weights every day. And you may, but I bet you do it on different muscle groups when you do it, because if you build on the same muscle groups every day, you won't ever get built. You'll be breaking down. So same thing on runners.
Is it, so like, my mom said something about, insanity now, like, it's bad for you because you use the same muscles you're using.
Oh, you're not supposed to do insanity every day.
Every day, and so.
It's a
like,
good
it breaks
option.
the- Yeah. It breaks
Throw it in there, for me, once a life, you know, anybody else once a week. You know, it's insane. Why you wanna do insane things, right? But she's exactly right, because you have to break these things down before they figure out what you want out of them and start repairing. So joggers never should jog every day. That's just total breakdown of their whole system. You know, jog 3 or 4 times a week, but you gotta have resting stages in there for repair and maintenance of the cells you just abused. And then once they figure out what demand is, they'll stand up to it. And then of course, what do? We push them a little further. Let's do more. We're never satisfied. So, now, with the information we have here, are y'all sure you don't have this in your set of notes I gave you? Is it not in there?
No.
I was thinking I pulled that out of a set of zoology notes, but it's probably my own secret set. I seem to have secret papers that I forgot I put together from time to time. Anyway, from this information, how do you explain rigor mortis? Some of y'all just went into a state of rigor mortis upon that question. It's like, mum's the word.
Calcium's not coming out to make the reaction happen anymore.
Calcium's not coming out to make the reaction happen anymore.
Your brain's not sending it.
So you're saying it's not, we're not gonna contract? You're really close,
You're dead, nothing's happening.
really close. That's lame. You're dead. Who cares at that point, right? Except the person paying the bill. You know, both y'all are a lot of right in both those statements. Since our cells do store energy, when a person, when we consider this body dead, does that literally mean every cell in it is dead at that point?
No.
No. All the cells are working together trying to maintain a complete steady state in this body. So when somebody's actually considered dead, would body temperature start going down at that, from that point slightly? If we reach a certain point, what do you think all the cells of the body's saying? We
It
gotta get
runs
body
low.
temperature up, right? So a muscle, to get body temperature up, what do we do? We shiver, right? Muscle contraction, shiver. And so we use the energy to try to contract the muscle to create heat. And we get it contracted, but we don't have the energy to not contract it. See what I'm saying? So we have the calcium available, it's out there. We have energy stored, we use it to try to maintain body heat. And when we use it all up, we end in a contracted state because we don't have the energy now to remove the calcium so we can relax. So, different scenarios here. If it's a cold environment, we're actually going to be in rigor mortis faster and we'll stay there longer. Make sense? We get there faster because of cold environment, your body temperature is going to drop faster, we use up the energy faster, we're there faster, but a cold environment, tissue deterioration is going to happen slower, so you're there longer. Now in a warm environment, like good quality roadkill on a 100-degree day,
You'll be good in a day.
you're pretty much toast and part of the pavement by the end of the day, aren't you? So, yeah, you'd hit rigor mortis slower on a hot day. You'd be there a lot less because tissue deterioration is gonna happen a lot quicker in a hot day. So temperatures plays a huge role in how rigor mortis kicks in and goes away. And the only way a stiff becomes relaxed again is by tissue deterioration. Isn't that what y'all wanted to come to school today, is learn about rigor mortis at 1 o'clock? Why not? Now you can understand rigor mortis. Does it make sense though? I mean, all your cells, I mean, how many of y'all go home a lot and you're tired? And you're, oh, see, she didn't raise her hand. You know, I hear this from my wife all the time. I've been tired all day.
That's how.
I've got to work out tonight.
That's how I feel.
I may think that, but I don't want to go work out. I'm tired. I said, did you just hear yourself? You're tired. Well, of course, I know the right answer. The more she works out, the more energy she gives her body because her body's used to that energy. And when she doesn't work out, the cells say, oh, vacation, I'm not going to make any more energy today. So you have a tired day. And it's much better to work out of a morning. Then metabolism stays hyped all day. Don't work out at 10 o'clock at night and then try to wind down and go to bed. You don't get much out of that. Some sweat. Not a good thing to take to bed with you. So that's where that stored energy. That's where that stored energy comes into play. Is preparing the cells to do more work, and then they'll be available to do it. Any questions?
What about cramps?
Do
So
what?
you get like leg cramps?
Leg
and stuff?
cramps. It's usually electrolyte imbalances more than anything else.
Not calcium or anything.
Not
It's like
calcium.
potassium, ain't it?
It's more potassium than anything. Some sodium can be involved in that.
Is that why when they say after your body cramps that you're like dehydrated and everything?
Yes.
Your electrolytes?
Yeah. Electrolytes either are not there or can't get there because of dehydration. And potassium's the biggest thing you'll see people in. And of course, Gatorades and things like that not only supply a lot of electrolytes, but they also supply glucose into the system. My son's on me all the time. I love fruits. I'll eat about any fruit out there, and if there's a bushel in front of me, I'm liable to eat the whole bushel. You know, eat a half a watermelon before I go to bed. It's no big deal for me. I just love watermelon. I sit there and eat it, and that's the absolute worst thing I can do. Because watermelon is watermelon. It's water and glucose. That's what it is. Water and glucose. What does glucose turn into if you don't need it? Fat. So I eat watermelon, go to bed and get fat.
Well, if you lay down on it, you're gonna get that anyways.
So, any way you look at it, but he said it's a great fruit to eat, like people that exercise a lot. You just drain yourself of a lot of glucose, and you can go eat a whole watermelon after that, or half watermelon, whatever, because you're just replenishing what you'd already used. In my case, you're adding to what you haven't used in years. So there's a big difference. I've been storing it for a long time. I'm waiting, so I don't know what's coming next. We mentioned cardiac muscle. I want to briefly throw that up. That's a cardiac picture of cardiac muscle. This is also on my website. Looks like the picture in your book, don't it? Amazing. Probably the same picture.
Are we gonna have a test over the tissues?
Eventually in lab. We'll go over all of them in lab before we have that test though. Now, the difference in cardiac and skeletal is this. They're both striated, but skeletal is involuntary, or excuse me, skeletal is voluntary and cardiac is involuntary. In other words, cardiac works on its own. What would happen if we sit around and tell our heart to beat 70 beats a minute?
We forget and die.
We'd be in trouble. That's why I'm too tired tonight. That would be our excuse. So obviously we know where its specialty lies, but it is considered striated, but it is involuntary compared to voluntary. And they did, or I have this is also cardiac, but they did it with a different stain, and you can see the cross striations better in this one. Cardiac muscle also have what's called intercalated disc, and you can see these real easy in this one too. There's one I'm missing. Smooth muscle. Where's my smooth muscle? In here somewhere. This is smooth muscle. Smooth muscle is found surrounding vessels, surrounding respiratory tubes, bronchioles, bronchi, and it is not striated. That's why they call it smooth, and it is involuntary. Now, you find it surrounding your digestive tract. So when you swallow food, it's smooth muscle that takes the food down the esophagus into the stomach. You ever swallow that chunk of peanut butter and you feel it all the way down? Looking for something to drink. It doesn't happen real fast. It moves slowly. It's called peristalsis. When we get to the digestive chapter, which I think is coming up here pretty quick. And then it gets to the stomach, and then comes out of the stomach and goes through the small intestine, and that's called segmentation. Same thing. It's smooth muscle contraction. It's also very slow. So smooth muscle, it specializes in very, very slow, rhythmic type contractions. Cardiac muscle is very consistent contractions, right? Skeletal muscle is fast, but it doesn't last. Smooth muscle is slow, but continuous. I mean, it gets the job done. So they all have their little specialty. You know, if we put skeletal muscle in the place of smooth muscle, and you ate something,
You'd be going to the bathroom real fast.
well, you'd have to eat sitting on the toilet. Or slap the person next to you on the way to the toilet. What'd you do with my food? Well, it's already come out the other end. You better hurry. So we need the, you see how they specialize though? We need these things. We need this to be slow, so we can get the good out of it before it gets through the system. So, you know, back in the, you've all heard these stories of our grandparents having no shoes and eating turnip greens and walking uphill both ways to school. We've all heard these stories. Well, you know, back in the Depression, one of the favorite foods that they would feed their kids is boiled okra. You ever tried boiled okra? I love boiled okra. It clears my house out every time I cook it. The wife and kids leave. But it's more for me to eat.
The only good way to eat okra is fried.
Probably say fried okra.
It probably stinks just as bad as
I like it
cabbage.
pickled, I like it fried, I like it boiled.
Boiled cabbage and
Oh,
fried
I
cabbage is amazing.
This is what they used to do in the Depression. They'd line up the family, didn't have much food, you know. They tie a string around boiled okra and feed this one, pull it up, feed this one, pull it up, feed this one, pull it up, and then they put it back, and then they'd use it again later. That's how they fed their family. That's how slimy the stuff is.
That's
But you can
nasty.
use vinegar to cut the slime, it really goes down good. It's good stuff. All right, now that I've got you grossed out, we are finished with this chapter. And we are in chapter 30.
Short chapter.
So on chapter 29, we only need to know about the muscles, or will we need to know the
Well,
whole
the stuff
chapter?
we covered the other day too.
Okay.
Chapter 30 is homeostasis, which osmotic regulation, excretion, and temperature regulation. A pretty neat chapter. It'll take us probably more than 2 class periods to get through this one, but there's quite a bit of, when you think about osmotic regulation, or if you think about the kidney, I mean, that's where we're at in this, for us, is the kidney. Your kidney sees 50 gallons of blood a day. How much blood do you have in you? 5.5 liters? 5.5 liters? It sees your same blood a lot. It's the organ that sees the most blood all the time. And it makes a lot of adjustments for us. If it sees too much volume coming through, it'll get rid of some. If it don't see enough coming through, it gives off regulators that conserve what we have. It prepares us for all the situations, and it does it, gosh, it does it every minute. We actually will filter through our kidney 125 milliliters of filtrate per minute. 125 milliliters. How many milliliters in that bottle right there?
355.
Milliliters? All right, so 355, so we filter through our kidney 1/3 of that bottle every minute. Every minute. How much of that, 125 milliliters per minute, actually turns into waste that might turn into urine? Per minute. It's all right to be wrong today. We want to get it right for the test,
I was
but
fixing to say either maybe half or 25%,
maybe 25%?
or maybe half.
Does that count for what you sweat out?
3/4 of it turns into urine? Do what?
Does that count for what you sweat out as well?
All of mine.
We're not talking about sweat. We're just, yours is what?
All of mine does. When you get my age, I'm in the bathroom all the
It
time.
just goes. That's why they make the pens.
Oh, wow.
Yeah, we're getting there.
Yeah, I'm not.
About 1 to 2 milliliters per minute turns into urine. If 3/4 of it or half of it turned into urine, your obituary would say they peed themselves to death. It'd be an awful way to go, wouldn't it? What happened to them? They peed themselves to death. The old kidney just didn't hold out. It just. So there's a lot of neat statistics that goes with this, and I mean, that in itself is just, it's not something you sit around and think about. But I think you probably, how many of y'all exercise? Some at least. Okay, 2.5 of you. Half the time, maybe. But do you notice you pee less when you work out because you do sweat? And all sweat is diluted pee. That's all it is. It's water with salts and urine. And you see these old baseball hats, and you're wearing a good clean one. You see these baseball hats with rings around them? You might as well fill them up with pee and let them dry, because that ring around it is dried urine. It's urea crystals. And that's why it smells like it does. Your hat smells like a urinal. Well, it is. Huh?
So that's why it's always brown.
Yeah, that's right. It's always brown. But we don't think of things like that. Play high school basketball, any of you? Play post? Get in there and sweat with them? Y'all's in there in the lane peeing on each other all day. That's what you was doing when you was rubbing sweat on each other. We don't think about these things, but that's what's happening. I mean, that's just our body finding ways of excreting things. Let's look on page 669 and look at some of their terminology here. The first thing they list on the page is talking about negative feedback, and negative feedback is the primary way that our system maintains homeostasis. Let's put us a definition of homeostasis. It is a steady state. A steady state. Some books will call it a dynamic constancy. Steady state or dynamic constancy. It's really, if we take our blood pH, our blood pH is supposed to be 7.4. What's neutral on a pH scale?
7.
7's neutral. What's neutral on human blood pH scale? 7.4. All right, the realm we're supposed to stay in is 7.35 to 7.45. That's not a huge realm, is it? Yet we stay in that. And if we don't, then if we get above 7.45, the body does things to get it back down. You'd think, well, I drink about 3 glasses of orange juice, that'll jack that acid up, you know. It doesn't bother it. The good news is 65% water, it's all diluted out to where a little bit of orange juice or a little bit of something that has an acid coffee is really acidic. It doesn't just screw your whole system up to drink coffee. People drink 8 or 10 glasses a day and they don't screw their system up. So if it gets below 7.35, then we make adjustments up. If it gets above 7.45, we make adjustments down. In physiology, I use this terminology. A negative feedback is opposing, where a positive feedback promotes. And the test questions are even ran to where, which of the following would be a positive feedback? Would increase be a positive feedback? It would be, because if we're already increasing and we promote that increase, that's positive. What about decrease? Going in the same direction, that's a positive feedback. But if we're increasing and we decrease, increase, or decrease, we're opposing, aren't we? So that's negative feedback. That thermostat works off negative feedback. It's got a realm, and when it gets out of the realm, pops on a system that either heats or cools, whichever direction we need to go, and fixes that and keeps it within that realm.
Negative feedback is opposing and positive feedback was what?
Promoting. If you're going in the same direction, it's positive feedback. If you're going in the opposite direction, it's negative. Now, majority of our cases are negative feedback. Let me give you a couple positives. A couple of positive feedback. The most commonly noted in all the books are both in the female body. Number one, it would be in the first half of the female cycle. An increase of estrogen on day 12 would cause a surge in luteinizing hormone on day 13, which would cause ovulation on day 14. Increase, action. Increase. The other case would be during labor, during child labor, you'd have an increase of oxytocin, which would cause an increase of uterine muscle contraction. So increase oxytocin, more muscle contraction. More muscle contraction requires more oxytocin. More oxytocin, stronger muscle contraction. This is like a vicious cycle, right? But we finally get feedback, don't we? Somebody's gonna get hurt, or this baby's getting out somehow, right? And it was somebody else's fault, and we're gonna kill them when we're finished. I've been on the receiving end of that. I have scars. So those are both positive feedback because they're increasing to get a result, or decreasing to get a result. All right, looking on 669, how marine invertebrates maintain salt and water balance. We gotta think a little different on some of these because this is really not our environment. So we gotta think like a fish. You gotta think like a freshwater fish, think like a brackish water fish, think like an oceanic fish to get these in our mind. But here's some terms. Because such animals are incapable of regulating osmotic pressure of their body fluid, they are called osmoconformers. So they don't regulate very well. They have found an environment they can live in, and they just conform to whatever that environment is. So a conformer's pretty easy. They don't make adjustments, they live in it or they don't. Animals that are restricted to living in narrow salinity range. These are stenohalon. This would be a freshwater animal. Freshwater has salt in it, but it's not high in salt. If we put them in salt water, they probably wouldn't survive. You don't put a largemouth bass in the ocean. See, you don't take a halibut and put it in fresh water. You know what I'm saying? So the stenohalon's a narrow, restricted salinity range. Here, animals must cope with large and often abrupt changes in salinity as the tides ebb and flow and mix with fresh water draining from rivers. So we have fresh water mixing into the oceans all the time. This is called brackish water. On the next page, we have this meaning that can survive a wide range of salinity changes, mainly by demonstrating various powers, is osmoregulation. So there are animals that can make adjustments to their salinity range. So there's animals that live well in brackish water. Maybe they get a little close to the ocean. Water's a little saltier. They survive. Maybe they go all the way up into fresh water. It's not so salt. They're still surviving.
Wouldn't that
It's
be
still,
like the bull shark?
the bull shark makes that adjustment well. It's one of the only ones that can. You've been watching river monsters, haven't you?
Oh, I love it.
I do too. My two come in and they're watching some goofy cartoon. I said, "Give me that flipper," and Faith will say, "Let's watch River Monsters." We're good for river monsters. So the first regulator they talk about is a hyperosmotic regulator. And this hyperosmotic regulator means that it maintains its body fluids more concentrated than surrounding water. All right, so this would be a freshwater fish. When you hear the term hyperosmotic, think of the fish having more salt in it than the water around it. The fish is hyper, the fish is saltier. So this is what happens. Here's a fish swimming around in fresh water. Okay, as it swims around in fresh water and it has more salt in it than the surroundings, this fish actually gains water. Everywhere salt goes, water falls. So if he has more salt in the body, he's literally swimming in water, absorbing water. Now, that in itself could be a problem. So the fish's kidney is going to excrete the excess salt, right? Fish do pee in the water. And so it excretes the excess water, but it also loses some of the salt in the system. Just like if we drink a lot of water, we'll pee a lot of water. That's a real common rule. The more you drink, the more you pee. Thought I'd throw that one in there. We're going to lose that salt too. So to get it back, they actually have salt glands that actually retrieve salt from fresh water and put it back in the system. And now they're right back to where they started. They start gaining water, they pee out extra water, lose extra salt, salt glands get the salt, bring back the system, and we're constantly monitoring this. It's just constant. And that's a hyperosmotic regulator. Go over to 671, and I think, they use a brackish water shore crab as the example on the hyperosmotic regulator. But you look over on the next page, and they talk about marine fishes in a hypoosmotic regulator system, meaning the fish has less salt in it than the ocean. How many of y'all have been in the ocean? It is salty, isn't it? I mean, it's so salty when you come out, you don't even need a salt shaker for supper. You just flick it off your arm. You don't come out of the ocean feeling clean, do you?
What do you feel like?
Gritty.
I'm
Very
not sure.
dry.
You feel like
Dry.
you're loaded with
Paper.
sand.
You want lots of lotion.
Going to, like Curve Beach and coming out with all the sand and stuff around your ankles and your feet.
Why do you need a lot of sand? That kind of explains sand. Why do you need a lot of lotion?
It dries out your skin.
It dries out your skin. Because there's more salt in the ocean than in your body. It's sucking the water out of your body. You swim in the ocean, you become dehydrated. You live around the ocean, you become dehydrated. I've been around the ocean and not in it and have salt all over my skin. I mean, it's in the atmosphere. So, in these little fish, in their case, this doesn't stand for sharks, but this stands for all other marine bony fish. In their problem, they're swimming in a watery environment and becoming dehydrated. Now that's just stupid, but that's what happens. So here's a fish swimming in water, becoming dehydrated. So he's thirsty. Does he have a little freshwater straw he can go hook up to? No, he drinks salt water. Well, they tell us not to do. Don't ever drink the salt water, right? He drinks the salt water. It's the only water access he has. So he drinks the salt water in. Now he has way too much salt, right? He got the water, way too much salt. So his kidney excretes the excess salt back out into the ocean, only to start the process over again, right? Now he becomes dehydrated, he drinks the salt water, we get rid of the excess salt. You see the pattern? So they're constantly monitoring this, they're regulating their surroundings.
If that
Now-
be the case, what does salt water do for you, like when you get strep throat? Some people will tell you, to gargle with salt water.
The salt being more abundant outside of the bacteria that's causing the strep throat dehydrates the bacteria and kills it. Back in the olden days before freezers, when we had smokehouses, they always salted that meat down, or they used a sugar base. Sugar and salt both will draw moisture out of bacteria and kill them. When you eat at Mexican restaurants, the food's really salty. That's so you don't get food poisoning. And you'll drink more pop, which is their biggest profit. It's about 200% profit on pop. So, costs them about less than 20 cents for whatever cup of pop that is that you paid, what, $2.75 for now?
Yeah.
So, that's why salt works for that kind of stuff. It dehydrates the stuff around it. Anybody ever make homemade ice cream? What'd you do with the salt water and stuff in the freezer when you got finished with it? Whatever Dad did with it, you just ate the ice cream?
We had to turn it.
Yeah. I have arthritis in my arm for turning ice cream. That's when I went and bought an electric one.
I said,
Just plug it in and just allow it and eat.
So you take the salt, this salt water, and wherever you throw it, it kills the grass, doesn't it?
Yes.
How'd it kill the grass? Dehydrated it. That's exactly what it did. And it don't grow back for a while either. It's like dehydrates the soil and everything else. It's a sterilizer. All right, there's how it goes. Now, at the bottom of 671, the salt composition of shark's blood. So let's throw a shark in here. Is similar to that of bony fish, but the blood also carries a large content of organic compounds, urea and TMAO, which is trimethylthiamine, something. Lethylthiamine. I believe it's got an ethyl in there somewhere. Anyway, what this does, see, our kidney will excrete that excess urea, and the average fish's kidney will excrete that excess urea. But the shark's kidney realizes that if it hangs on to it, it don't have to deal with all the same thing this bony fish does. So the bony fish, where it's becoming dehydrated, not the shark. Now, here's the side effect. If the shark stops swimming, it'll start sinking. Buoyancy is a lot less for the shark. I mean, sharks don't quit, do they? They just go on all the time. So it works out good for the shark because they're not using a bunch of energy on this exchange of water back and forth and excreting back and forth. They just hold on a little more urea. The urea, which is a salt base, equivalates inside and outside, so there's no movement of water between that shark and its surroundings. So it pays off for the shark. Look at over 672. Get into a little bit of terrestrial animal stuff here. We're dealing with terrestrial animals. I mean, wide variety of comparisons we can throw out here. You look at us and think, well, we're considered terrestrial, but we have access to water. If we were put in a real dry environment with not much water, we probably wouldn't last very long because we're not adapted for a desert type situation. Would a camel be more adapted? Sure. They in the research, they said a human kidney can concentrate 4.2 times that of blood osmotic concentration. The urine would be concentrated 4.2 times that of blood osmotic concentration. A camel can concentrate its urine 8 times. So more than double. You think, well, that's pretty good. But a gerbil, anybody ever have a pet gerbil? Can concentrate its urine 14 times that. Now, that cage always smelled good if you didn't clean it, didn't it? But that's not, here's the one that gets you, is the Australian hopping mouse. Now, there's you a pet to have. It can concentrate its urine 25 times that the blood osmotic concentration. But look where these animals live. Compared to us, we have plenty of water. The Australian hopping mouse lives in an environment that there is no water. It gets 10% of its water from the food source that it eats as free moisture. The other 90% of its water comes as metabolic water broken down from the food source it eats. It doesn't have a whole lot of water to go drink out of. Not there. And all of those, as they get better at what they're doing, because of their environments, that's how they adapt to it. So, metabolic water's mentioned there. Kangaroo rat, they throw that in there, and they give the same stats for the kangaroo rat. I like the Australian hopping mouse better. It's just a better term than kangaroo rat. That's a big rat. Let's see, dropping on down toward the bottom, we see that terrestrial insects, non-avian reptiles. What does non-avian mean?
Not birds.
Not birds. I don't know why they shouldn't say reptiles other than birds, but no, they had to say non-avian. Now we're smarter, right? And birds have no convenient way to rid themselves of toxic ammonia. Have you ever seen bird poop on your vehicle?
Makes you mad.
Today's time shouldn't be that bad. We got the clear coat on there to protect us, right? Back in the day when they had a paint job, no clear coat, they'd eat right through it. Because with no way of getting rid of urea, see, we sweat it out or we pee it out. A bird does not have that capability. So a bird makes a uric acid paste. So when you see a white streak in bird poop, that's uric acid. That's what's eating a hole in your paint. Yeah, or the windshield or whatever. Get some on your finger and see how it burns for a while. It's uric acid is what it is. It is non-toxic, almost insoluble compound, but that's what it is. Now, marine birds and turtles have evolved an effective solution for excreting large loads of salt. Now think about this. If you've been out around the ocean, we've seen all these shows on these marine turtles coming in and landing buku's eggs and all. Do you ever think about their eyes open all the time in that kind of salty water? How would your eyes feel if you had this open all the time?
You wouldn't have no eye.
What about all the food they eat? Everything in the ocean should die of hypertension because they eat salty food all the time, right? What about seagulls and petrels and all these birds that eat seafood all the time? It's like, I'll have a little salt with that. Yeah, you'd think they're all gonna have hypertension. But what they have a specialty is a gland that excretes this excess salt. They consume a lot, but they get rid of it. Seagulls. You ever been around seagulls much? They're the nastiest birds out there.
They're mean.
Well, they're mean, but they're still nasty. Nasty in another way, I guess. But they don't just sit here and poop. They poop all over everything. I mean, they poop over there. They sit here and they poop over there, poop over there. It's just big splatters. And if you ever got close enough to them, with some of them probably trying to attack you, you ought to get a look at them. Their eyes are bloodshot all the time. It's like, these gulls have been on drinking bench forever. But they're bloodshot all the time because their salt-secreting gland, this is where I think God has humor, he puts it in the corner of their eye, salt-secreting gland in the corner of their eye to make their eyes bloodshot all the time. So they have not only the crap everywhere, and they have bloodshot eyes, but perpetual runny noses all the time because it comes out of the corner of their eyes and goes through their nostrils and keeps their nose cleaned out all the time. So they're snotting all over everything, and pooping all over everything, and you wonder why they're fussy all the time? It's like, this would be a good bird to play a trick on. And so, yeah, these salt-secreting glands make this capable, and they mention those at the bottom. Look at the invertebrate excretory structures. Contractile vacuole. We're not going to spend a lot of time on these, but when we say invertebrate, we're looking at some of the things we're going to look at lab this week, the protozoans. At least some of us will look at them this week. No guilt tripping intended at all.
Not at all.
But if I ask you, and when we get back to the protozoan chapter, if I ask you, what's the means of water balance in a protozoan? You're going to say contractile vacuole. So they're going to repeat themselves in 2 or 3 different chapters. Here they're telling us. We'll see it again when we get to that. I think it's chapter 9. But that's how they take care of water balance, is a contractile vacuole. Now, what is their kidney? Their kidney is a nephridium. They have it listed. We have a kidney that has 1,000,000 nephrons. A nephridium is a fragment of a nephron, basically. It's very incomplete compared to ours. But each one of our kidneys has 1,000,000 nephrons. 25% of those must work for our kidney to do its job. They have, let's just say, we can picture it better like this. Let's just say they have 1 nephron, that's their kidney. Makes ours pretty significant, doesn't it? So we have what's called a metanephric kidney. Meta means many nephrons in our kidney. Metanephric. Look over on 674. Arthropod kidneys. There's 2 or 3 things going on here with arthropods. You have antennal glands, you have Malpighian tubules, and I don't see them listed here, but somewhere in there, there's actually I thought I saw a picture of it earlier, what's called a green gland, and some crayfish will have a green gland. But antennal glands, Malpighian tubules, that's their excretory organ for arthropods, which are crayfish, crabs, shrimp, grasshoppers. That's your arthropods. Takes us over to 676. And this is where it really starts the vertebrate kidney. This is where we're gonna start breaking down into our particular kidney. And I'm gonna kind of put a drawing up here that gets us started on it. I don't think you have this drawing in your notes, but I'll have another one that I'll put up on the board. If I think about it, I'll run some copies, but anyway. Like I said, when I described our kidney, there's 1,000,000 nephrons. Each nephron has its own job to do. And what we're gonna put up here is the sequence of blood flow coming in to the nephron. Now, some of it will stay in the bloodstream, some of it shifts into the nephron, and the nephron picks out what it needs and sends the rest back to the bloodstream. We have interchange through active transport and diffusion through this process. But what we're gonna be looking at is 1 nephron out of 1,000,000 in the kidney doing this job, okay? So, we have what's called, I'm gonna try to label these as I go. Bowman's capsule. We have what's called the proximal tubule. Get another pen here. This is called the loop of Henle. This is called the distal tubule. And this out here is just a collecting duct. It collects from several. So, Bowman's capsule, proximal tubule, loop of Henle, distal tubule. This is all the components of 1 nephron. The bloodstream coming into it, first set of capillaries, you have an arterio, it's an afferent arterio. Comes in and creates the first set of capillaries, which is called the glomerulus. Now, this is where pressure filtration takes place. In other words, the pressure in our blood flow coming into this is at a higher pressure than what's out in this nephron. So as it comes in and pushes, it pushes everything out here, except, should you ever find red blood cells in your urine?
No.
Not a good indication, is it?
No.
What about protein?
Yes.
Should you find protein in your urine?
Yes.
Depends on what I've been drinking, right? You really shouldn't you'll find some, there's a minimum number, but most of your proteins are too large to actually get through the back of the Bowman's capsule. Everything else it pushes out there. Now think of all the things that we might actually need to use that's pushed out there to be waste. What about glucose, sodium, potassium, chlorine, electrolytes, all these things, they're all out here now in this. And then this first proximal tubule, 60 to 65% of the things we know we need is sent right back to the bloodstream. So we've got the glomerulus coming in. Now, the equivalent bloodstream here is the efferent, let me think here. Yeah, efferent arteriole. Then we go into a second set of capillaries right through here, which is called the paratubular capillaries. And then we get into the renal artery out here, or renal vein, excuse me. Renal vein out here. So immediately, this is how good our kidney is. When it sees 125 milliliters of filtrate per minute, when it sees 50 to 55 gallons of blood a day, it's making adjustments every minute. This minute, it may say it needs to keep some sodium. Next minute, it may say to get rid of some sodium. But 60 to 65% of the stuff we know we need immediately goes back to the bloodstream. Glucose, electrolytes. If we're dehydrated, let's throw some extra water in there. Throw some extra salt in there. At the end of this, it'll really specialize in sodium reabsorption. What follows sodium? Everywhere sodium follows, water follows. Or sodium goes, water follows. So you have the descending limb and the ascending limb of the loop of Henle. If we had to summarize the loop for our purposes in zoology, we would do a summary here. One thing would the loop be specialized in? Water reabsorption would be the one thing we'd say. So we can apply this back to some of the animals we've been talking about. Our loop of Henle, it'd be decent size. We'd have a loop of Henle. A fish that lives in water may not even have a loop of Henle. They don't need it. Freshwater fish, they have plenty of water, right? But that Australian hopping mouse, the biggest thing about his kidney may be the loop of Henle, because that's what helps them conserve water. The larger the loop, the greater conserving capabilities. So the loop of Henle, this one, if this does sodium reabsorption, what follows it?
Water.
Does water all the way down through here. And then the kidney turns it around and does salt all the way up to ascending, all the way up to ascending. So it prepares now to take in more what here? More water. You see, in fact, the books will call this a counter current multiplier. We counter salt with water, then more salt, and then more water. We keep countering the two until we reach the equilibrium we want. Counter current multiplier. I'll bring into play when we start this up on Thursday out here where hormones, this is the only place that hormones will affect the kidney and our ability to conserve more water if we're dehydrated. If we're not dehydrated, then let the water flow, we'll pee more, okay? If we're dehydrated, we have two hormones, aldosterone, and out here, ADH will follow, and they work together. Aldosterone reabsorbs sodium, even more of it, so water will follow out here. More sodium, more water. When we come back on Thursday, we'll look at kind of summarize this. I'll have kind of an overhead chart, or I'll try to come up with one between now and then. And go back over this a little bit, summarize it, hopefully put it to everyday use. And continue on from there. And we'll look at some more things the book has to say about it as well. Well, then we get into some good temperature regularly. I get to tell some stories Thursday. You're going to miss.
No, we meet in
I'll try to post a video.
We meet in here up there.
Thursday, let's see. Go ahead and turn that off if you don't mind.